Welcome back to another week where I explain the classwork. Today I'll be going over what we went over on March 4th. It was regarding free body diagrams. And so basically the scenario was, it was on an inclined plane and there was an object right here. So the box. And what we were supposed to do is first draw the free body diagram. Man, this does not look like a box. Let me draw that again. There we go. And so what we first have is the normal force that is pushing up against this box. However, we know that the normal force is perpendicular to the surface. When I first was doing physics in high school, I initially thought that normal force was always pointing up because before we were introduced to inclined planes, normal force was always pushing up on a flat surface. However, it's most important to remember that normal force is going to be always perpendicular to the surface. And so instead of it pointing straight up, the normal force would actually be pointing this way, more towards the right. So that's our normal force. And then I think this is a question where we were to ignore friction. And so we don't have to worry about this friction force that is pointing upwards, that is going against the momentum of the box, or the motion of the box going down. And I'm pretty sure the ball was at rest. No, the ball isn't at rest. We're assuming the ball is going down, but there is no friction. And what we're trying to find is the acceleration. Okay. And acceleration of the box in a certain direction, but we'll get to that later. The box is, and then the weight of the box, mg, or w. I don't like this marker. Okay, so now that we have the free body diagram of the normal force that is going perpendicular to the surface and the weight, which is mass times the Earth's gravitational pull, which is going straight down, you have your free body diagram. However, you want to add components to this vector right here, or is it a vector of this force? I just call it a force right here, where it has this component going this way and then a component here going this way. And so we were given that this is 30 degrees. However, since we know this is a right triangle, we also know that this is 60 degrees. Because, well, 90, yeah, because it's 180 degrees in a right triangle, 90 plus 90 is 180. And so once we have this information, okay, first of all, I got ahead of myself. What we're trying to find currently is the acceleration of this box. And now when we change, or when we're looking at this equation, we want to simplify. We want to make sure that we solve this question as simply as we can. And so what we're going to do is we're going to make it so that this is the y-axis and then this is the x-axis. Because if we were to just continue using these two, this being the y and this being the x-axis, now the box is moving in two planes. It's going in this direction. It's moving both in the y and in the x. However, if we set it up like we did right here, where we make what is perpendicular to the surface, the y, and then what is going in this direction, the x, we're now only solving in one dimension. It's only now going in the x-axis. And so, since it's not moving in the y direction, we know that the net force of y is 0 newtons. Because it's not moving, it's at rest, it is 0 newtons. However, what we're trying to find now is the force in the x direction. And so m, and then acceleration with respect to x. And so once we have this, now we can start, thinking about, okay, how are we going to go about solving this question? Now, the normal force doesn't have any force in the x direction. However, when we look right here, the weight is pulling it has in, like we mentioned in earlier, the components of the x direction and then also the y direction. And so to put it simply, since we know the degrees, we have the weight first, or we could, you know what, to make it simpler, just mg. And now using these degrees, now since we got this 60, we want to get this line right here. And so using SOHCAHTOA, we know that's cosine, because cosine is the adjacent. If we were to find it in the y direction, it would be sine, so opposite over hypotenuse. Cosine, and then the degree, 60, equals m/x. And also we have just basic algebra, cancel out the masses on each side. Now we got g cosine 60 as the acceleration. If you plug this in, if we use 9.8 cosine 60, you should get 4.9 meters per second squared of the acceleration in the x direction. And so that's the first question that we did. And I would like to do one more. And so that one included a kid on a sled, I'm pretty sure. And so the sled right here, and then a string right here. And so now we were to draw another free body diagram. We have the normal force that going perpendicular to the surface, act as if this is a hill right here. And then we have the weight, mg, going in a downwards direction. And then, now the kid, imagine a kid, let's see if I can draw, oh man. Okay, imagine a kid right here, and now the sled is at a stop because of this rope right here, which creates a tension force, Ft. I'm going to label this up here. And I'm assuming, and we were assuming that there was no friction, okay? But what we're here to find out right here, right now is, I'm pretty sure right now we weren't assuming friction. Yes, and so what we need to do is, or what we were told to find was f of t, so the tension force, mg sine theta. Now, why is it mg sine theta? Well, going back to what we kind of worked on earlier, the components of this weight. I kind of like the color coordination I did earlier. Right here and right here. And I think, I'm pretty sure we were given the equation of this angle, right here, being 30 degrees. And so with this given angle, we're able to have what the force is in the y direction, or the y direction, and also the force in the x direction, or the y direction actually being here and the x direction being this way. And so because we know that Ft is going this way, and then mg sine theta is going the opposite direction, but the sled is not moving, we can assume that these forces are equal. And so that's why we set this equation up right here. And we were given that the weight, actually I don't even know what the weight was, but we were given that the weight was 77, and then we have the rest of it here, 38.5 newtons. And so now we have our tension. We were also asked to find our normal force. Our normal force is the very same process right here. What is the force in the opposing direction? Because the object is not moving in neither the x nor the y. Of n equals mg cosine theta. So 77 cosine 30 equal 66.6. And so that's, there you have it. We have our force, our tension force, our normal force, and we're able to find that using these components of weight. And so, and kind of looking back, you could imagine this as the y and this as the x. And this, initially when I first started doing physics, it kind of confused me when, oh, if we're assuming that this is the x direction, then why are we using sine? Because for me always, it was like sine was always kind of attributed to the y-axis. However, the most important thing when you're looking at this is making sure that you're looking at what sine is with respect to the angle. And so sine with respect to this 30-degree angle right here is going across like this. And when it's going across like this, we know in this equation, how we set it up, it would actually be the x direction. And so those are just things to make note of, to be aware. And so that's all I have for today. What we did today, we went over free body diagrams on an inclined plane, normal force, tension force, components of a force in the x and y direction. And so if you guys have any questions or if there's any mistakes that I made, feel free to let me know, and I'll see you guys very soon.